So we'll get started. So Tony Smith has joined us from Australia in real life.
In real life, because at home it'd be 3:30 in the morning, and I'm not getting up at that time of the morning.
And I guess you guys can hear him okay?
Yeah, I can hear him fine.
Yeah. Introduce yourself.
So for the benefit of people, I've been coming along to the
Okay, guys, we're gonna get started.
Raspberry Pi group for about 9 years now. I first started when I was visiting London about 9 years ago. I came along one night for a pint and have participated via Zoom ever since. Except that getting up at this time of the year, it's getting up at 3:30 in the morning is a bit hard. So anyway, I'm in London. I'm visiting London for a few weeks. So I thought, well, we better come along again. So for those who don't know me, I work in a factory in Australia as a manufacturer. We make cable. We start off with raw copper and make cable all the way up to multi-core, complex hybrid cables, etc., and then turn them into looms, which go into all sorts of appliances, caravans, automotive, etc. So we have this problem of building a loom and then wanting to test it. So you've got a half a dozen cables, half a dozen wires, some connectors at each end, and you've got to make sure that when you're building thousands of them at a time, and we've done some of them where we've done in batches of 10,000, it's really easy after a while to make a mistake. And when in mass manufacturing, when you make a mistake, you don't make one, you make a lot. And so what I'm showing here is a test set for testing cables and looms. Now, a loom can be just a simple, 3 or 4 wires, connector at each end, very straight, but it could have a T-piece, a T connection in it. It could have multiple connectors. It might be connectors on one end, and the other end might be just bare cut wires that are going to be cut, stripped, and then soldered into something. So we have all these combinations. So I'm looking at building the next generation of a Raspberry Pi controlling a series of I/O devices. And so in this presentation, I'm talking about how I've used a Pico or Picos. I'm going to get up, straight up there.
Yeah, to the right.
Oh, okay. So what I'm checking for is swap wires. The person who's assembling it has put the wrong wire in the wrong hole in the connector into the housing. We've got an open circuit. The pin hasn't been pushed in fully, and therefore won't form a circuit. We've got short circuits. The wires have been damaged and the insulation has been stripped off, and we've got a short circuit between 2 wires. And we can accept spliced wires, 2 or 3 or more ends, and fly leads. And so at the very bottom is a typical screen we would run, and you'll notice this is sitting on a 22-inch screen in front of an operator who's testing. They don't need to look up. They can see in their peripheral vision either red or green, and they know there's no mistaking that they didn't read the test set. So we've got certain information about it's the model they're testing, so they know that the test program is correct for the product they're making, and they can quickly see. And then in the red one where it says error code, we sequence the wires. If you had 10 wires in the loom, then it will be from test 0 to test 9, and they can tell which one of those 10 wires is creating the fault. And traditionally, we've used, and something like 10 years ago, we started off using an MCP 23017, which is an 8-bit device. It's got 2 8-bit parallel ports on it, and we would wire them up as 8 out and 8 in. And so each card gave us 8 connections. So if you like a loom with, say, 10 wires, it's got 20 points. We had to have multiples of these cards to do a simple 10-wire loom. And so the thing is, we would start stacking them up. They're large, they're difficult to mount, and whoops, go back. The difficult amount and limited to 64 IO. So effectively it limits us to say 32 wire loom. We've got jobs coming up where we're doing 100, 120 wire looms. This gets complex. I'm going to have to start putting switching in, I2C switching. And so there's another way of doing it. There's a Pico. So it's a 2350B, which is not distributed through the Raspberry Pi Foundation. It's the second source supplier. So it's a stamped version. I bought it at a solder party in Sweden, and it gives me 40. It's got about 43 IO in it, and I'm using 40. And I put up the first 20 on the bottom DB25, and the second 20 on the top DB25. And this particular card has been set up by Solder Party to work in CircuitPython. So where I've used Picos before in MicroPython, I had to come across and use CircuitPython for this one. So it's USB-C powered, and I simply just put a cable between the Raspberry Pi and this card. The Pi powers it and communicates with it. And you'll see a series of pull-down resistors behind the DB25 connectors. That's associated with this issue that the Pico has got, where it doesn't properly pull down. So I added my own pull-down resistors, and read about that literally days before I committed these PCBs. So it was a quick redesign. And so you can see, and what I was able to do is through CircuitPython assign the GPIOs around, starting anti-clockwise, starting the bottom right-hand side, and just GPIO 0, 1 through all the way over to the diagonal corner GPIO 40. In fact, that's 41 IOs, and I actually this idea of counting from 0 drives me nuts. So I got 41 IO, and I go from GPIO 1, GPIO 40. I understand the reasons why and all of that, and I fully support it. So if I can avoid it, I do. So the connections are simply a USB-C on the Pico to a USB-A on a Pi. And if I've got multiple of these, up to 10 Picos, I put it through a USB hub. And I've got an externally powered power supply feeding an externally powered USB hub. That's supplying the power, the 5 volts to the Picos, and the communications is through the hub back to the Pi. And that works fine. And so the code I'm running in CircuitPython is simply this. I configure all the IOs as inputs, and then I just poll the serial port, and I'm looking for commands. And you can see there, it's saying here, else if data and lower says just put everything to lowercase equals read. So I will send it, the Pi will send this 4-character string read, and the Pico will go off and read all the IOs here and send it back with a simple statement, print the read function. If I say clear read, it will turn all the inputs, all the IOs to inputs and then read, because I may have had, or I don't know the state of whether I've turned some of the IOs into output. And so I just turn them all to inputs and then read it. And I have a series of commands, which I'll show a bit later, it's in the Pico that responds to the appropriate commands sent by the Pi. So the read command is nothing more than I set up a variable with, strange this, 41 data elements, and I count and I read from 1 to 40. Well, what I'm also doing is I'm sending back in the first byte a value of 5. So when I've got 10 of these hanging off a pie, I don't want to have to go and read every input of 400 inputs to work out which one is a 1 and which ones are a 0. Because it'll be a sparse matrix coming back, I can ignore, by just looking at that first variable, I can tell whether the anything in that whole card is zeros. If they're all zeros, I'll just move on, just by looking at that one variable. And then I just return the function value back to the, and they're the simple commands that I'm running. I've got turn all the inputs to input, read, clear read, which is turn them into inputs and then read. Out read is turn one output on and then read. And what I'm doing is I'm sequentially going around this loom, turning one output on at a time and seeing what else comes on. I can just turn one output on, and I can also check 0, just check all the inputs are logical 0. And that's as simple as that. And the rest of the processing is done in the Pi. And in the Pi, all I've got is I'm just using Pi serial, and I send a serial command, I send it out and then read I just read back what the Pico sends back. So it's a very simple communication. The Pi is controlling, and the Pico is responding. It's just polling around. And I can do a single card several hundred times a second. Even in Circuit Python, it's fast. I do have the capability of putting this all in machine code and then compiling it if I really want it to go faster. But at this stage, I've not needed to. It's more than adequate. So it's as simple as that. And if anybody wants more detail on what my code is in the Pi, I mean, you can talk to me outside of this meeting and I'll happily share bits and pieces with you. I don't know if there's any questions.
Can you look in transference? I mean, what there's a bad joint that is got a bit of resistance.
So I'm not testing for I'm not injecting current. So some looms we might need to inject 10 amps and then do voltage drop tests. We're not doing that. We're simply doing a continuity test. Have I got the right pins connected to in each connector? We're assuming the resistance is low. Now, a lot of these looms are actually put together. These are all machine crimped wires too. We don't hand crimp anything, and you get high reliability with machine crimped. Either a machine that will do. I mean, we can take a wire, take a 1,000-meter roll of wire, put it into a machine that will cut it into, say, I don't know, a meter length, 500 millimeters long. Cut the wire, strip both ends, put terminals on the end, and do it under a second, and pump them out fast. Or we can do them by hand, in a sort of feeding in one at a time into a machine. But either method is highly reliable. They're extremely consistent. So the idea of saying, am I looking for one crimp that's been a bad joint? I've eliminated that through the manufacturing method. So this test set is not designed to go looking for resistance in joints.
So humans, what are they doing then? So when you get all the wires crimped on both ends, and then they put into connectors, or what do humans actually? How do humans get involved in the process? So
yes, it's taking a maybe say 10 wires in 10 boxes in front of you,
yeah,
and connecting them in the right sequence,
right,
in the right combination.
And these are 10 wires in one cable, or how does it?
Yeah, so it might be, so it's a simple, 2 connectors,
yeah,
and 10 wires between them.
Yeah.
It might be pin 1 to pin 3, and there might be combinations,
yeah,
or it might be, a 10-way connector on the A end and 2 5-way connectors on the B end.
Yeah.
And so it'll be a Y-shaped cable.
And so the Pi has the essentially the wiring diagram, or
Yes.
so you can tell what the results
Yes.
should be.
Yeah. So we know what we expect, and we're doing a comparison between what we're getting and what we expect.
Right.
Now we can actually put the thing into self-teach mode, and as long as you're confident what you're actually putting as the master sample is correct, Because every time you do a master sample with the correct wire, you also do master samples with faults in them.
Right.
Deliberately doing at setup time, you actually go and check that you see a correct master sample, and you also see the errors.
So you can do a master sample and say, okay, let's just save all the data and you feed it back in, saying, here's your
Yeah,
truth table.
yeah. Or they can build its own truth table because you just plug the master sample in
Yeah.
and tell it to learn.
Okay. But this is an AI, it just sort of like, just figures it out.
Yeah.
Right.
Or I'll sit there and do it manually. Doesn't matter
Yeah.
either way.
yeah.
And of course, what I don't have here is showing us we do have a pie that actually shows you on a screen which wire to put where, and I'm working on with a camera to actually check that you actually did put the right wire in the right hole.
And what about the handling of the crimps themselves? I guess you just connect like the male and female together and just make sure it all.
So we might be making a loom that might be, say, a meter long. It'll have sort of, on the A end might have a plug, and on the B ends it might have two sockets or whatever. And so you're also testing that you've actually got the right housing on each end. You haven't put two plugs on, or
Right.
there are some
Some of the plugs coded as well, so you have like.
yes.
Yeah, you check the coding by just.
And so what I'll do is always put on the test rig is a mating half. So if you've got a plug, I've got a socket on the
Yeah.
test set, and you've got to put it in. You can check that it's not in backwards or upside down, and
So that's what the humans do. Or
the test set will do that as well.
Oh, okay.
And sometimes I
Is that
consider
something you bought, like the test set, or is it?
no, this is the test set.
Okay.
But also instead of using a connector to connect it, I might actually put a board with pogo pins on it, and you're checking that the pins are correctly inserted to the right depth.
Right.
And we particularly do that when you've got an earth pin on a mains device. You want to make sure the earth pin is 1 or 2 mil forward of the active and neutral pins
Right.
to make sure the earth connects first. And so we'll use pogo pins for that.
So is that all run by the same pi? Or
Yeah.
Oh, wow.
Yeah.
So it's just one part of the whole
Yeah.
much larger machine.
So this presentation is about how do I get all these IOs when you've got hundreds of IOs, into a pi.
Yeah.
And so I'm using Picos to do that.
Yeah. So what's your cost per board then? With the
Since I'm doing all the soldering and all the
yeah.
the Picos are even that Pico was I'm just converting it to pounds now. It's probably £5 or £6.
Right.
The circuit board is less than $1.
Right.
I haven't made it.
DB25 is not expensive.
Yeah, the DB25 is probably $10 or $20 worth. Probably £10 worth.
So why'd you go with the DB25? It's just something you just used to. You just use a lot of them or something.
No, that particular one's double stacked, so it gives me 2 of them.
Right.
It's all in one. So you plug it in and
Right.
solder it in one piece. So if you go back, you can see that this thing is stacked.
Okay.
It's physically one. So otherwise, if you had them as 2 separate ones, this top one would be levering on the solder, and you run the risk of fracturing the solder.
Right.
This bracket that it's part of the connector has got some spring clips that poke through the holes in the board, and you solder them in.
Yeah.
So that takes the mechanical load.
Right.
They're all on GPIO.
They're all on the GPIO pins.
You said they don't put that low properly.
There's a leakage problem with the original Picos where they will only pull down to about 1 volt. Because it's excessive leakage current from part of the circuitry. So they can fix it when they do the next upgrade to the PC, not the PCB, the chip masking, and that will get fixed in time. So I just put them in as a quick and dirty. It works fine.
Oh, okay.
So how does the price of this compare to your previous solution?
Oh, much cheaper.
Oh,
The previous one, well, the real issue here is in this thing. It's the time that it takes to solder all these through hole connectors through, and then the the cabinet, you end up with a big steel box, you end up putting the whole thing in.
Right.
And, you know, and ribbon cables and connectors, and I've got concentrator boards to take, you know, 3 of them into one connection, and it just gets out of hand.
You use it all the time. Do you have it on the new?
No. Yeah, okay, so I thought, let's take a risk here, and I have a rule. Never take 3.3 volts outside of the domain of the pi. So this thing works on 24 volts inputs and 24 volt outputs, fully opto-coupled inputs and outputs. So I completely broke that rule here, and I take the 3.3 volts off. I have lost 1 or 2 of them so far. So I might need to put a bit of I think it's static from the operator when they're plugging in a very long loom. I'm talking about something that's like 15 meters long, and they've walked this loom up along a table, and I think they've generated static.
Oh,
And as they've plugged it in, I think they've zapped the board.
oh,
I've lost 2 of them in 6 months. And coming away, I've left 10 spares. I hope they last. But I think what I have to do is put probably some transient suppression across here as well.
right.
Oh, yeah. But the size of this and the smarts of the Pico are so attractive. I'm prepared to persist with this and actually solve it rather than abandoning it now and saying it's not the way to go. I'll go back to the old way.
So what made you go with that one rather than standard?
IOs.
No, does the seller one have fewer published IOs out?
So this one here, I get 40 IOs out of it because it's the 2350B.
Yeah.
I get extra IOs out of that. I think I only get 32 or something out of the standard
Something
2350A, something like that, thereabouts. And I wanted to get up to an even. I wanted to get up to 40. They're available through these second source, you know, supplier. The cost difference is negligible, and it gets me up from say 30 up to 40. So I went that way.
So return on investment must be huge. I mean, someone that tests a relatively complex loom probably spend an hour or 2 if they can have this.
Oh no, we could test the loom in 30 seconds.
Yeah, with this. But
Oh, with
the
this.
human is doing.
It's like, yeah, you're there forever. Well, no, the problem is not time with a human; it's the errors they make.
Oh, yeah.
People have a known error rate.
Yeah.
And when you mass produce something, you multiply that error rate by the number you've made,
Yeah.
and you multiply that by the expense per unit of what's the downstream consequence of it.
Yeah.
It gets frightening.
Well, just recently I screwed up a loom on a train. I said, oh, yeah.
Yeah, you know, depending what you're controlling.
Cool. That's really good. Is there any
So-
questions from online? I don't know if there's any questions in the chat. Didn't see any, but I'm a bit behind. What are the frequency requirements of your loom? Sounds like only.
It's primarily DC. We're not doing RF. We're not doing coax cables. I would test them a different way. This is purely a very low frequency, you know, switching power on and off to lights. So if it's an automotive loom,
Yeah.
you know, it's on a trailer, it's switching the turning lights on and off.
Yeah.
That would be the highest frequency.
Right. And what version of PCB are you on?
That's Rev 2. It's pretty well what we're sticking with for now.
Yeah.
Rev 1 didn't have the pull down resistors.
Okay, that's the only difference.
Yeah,
So you didn't make any major errors in the volume version 1, just.
I
you
use
know about
I use KiCad. I'm so used to it. It's brilliant because you don't leave things out. You know,
Right.
you know, I run error checking and all that. And
And what do you suppose these things? Is it a steel box or do you put it in the That's really.
At the moment, it's stuck on the, underneath of the work table with a bit of double-sided tape.
Oh, nice.
Hang on, this is engineering. That's how you do it.
Nice. Cool. Any other questions? Or anyone wants to come off mute and ask a question? We're all good.
How many of these do you need per crimper? So do these go faster than the crimper, or because mounting them up
Yeah, yes.
takes one
No, so
step on?
no, we can do, the assembly time is longer than test time.
So only one step.
Yeah. Yeah. But the idea, actually what the time is, if I have one of these in a factory, you've got to take your product from your workstation across to the test station. It's the travel time going there and back. And so the attraction for this is I can put this in the back of a touchscreen Pi, so a 7-inch touchscreen with a Pi, and this one or two of them behind it as a very lightweight, self-contained test set that I can put on multiple workstations. They're not going the full 10, but just one or two of them. And that's something I'll be doing when I get back.
Very cool. Cool. So there's no more questions. Thanks very much, Tony. That was very interesting.